Use the rational zero theorem to find all possible rational roots for the polynomial function g of x equals 3x cubed minus 8x squared minus 8x plus 8. They want us to find all the rational roots. Well, the first thing we note is the degree of the polynomial. It's a third degree polynomial. That's the highest power on the variable, n equals 3, and that implies that we're going to find a maximum of 3 rational roots. We could find fewer, but no more than 3. Okay, step 1, let's come up with our list of rational roots. P over Q equals, okay, we're going to list all the factors of the constant on top, the number 8, and all the factors of the lead coefficient 3 on the bottom. So on the top, we're going to have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. That's all of them. And on the bottom, just plus or minus 1 and plus or minus 2. 3. Okay, so we found those. Now we're going to take all the numerators and put them over 1. Well, of course, we're going to pull the plus or minus out in front. Don't forget that. And then put all the numbers in the top over 1. And then continue the list with all the numbers on the top over 3. Simplify and throw out any values that are repeated. So we end up in the final analysis with plus or minus the set of numbers 1, 2, 4, 8, 1/3, 2/3, 4/3, and 8/3. So how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8. There's a whole bunch of them, and double them because of the plus or minus. Okay, now we will have to just start guessing and testing these numbers and hoping that we just happen upon one, because once you find one root, things start moving, things start happening with synthetic division. So I'm going to take a guess. I'm going to say, let's just guess where to start. We'll start with the smallest number here. Let's start with C equals 1/3. Let's see if that's going to be a root. We're going to synthetically divide the given polynomial by 1/3. There's no missing powers of x, so we'll just do synthetically divide 3, -8, -8, +8 by the C equals 1/3. Okay, bring down the first number, multiply 1/3 times 3 is 1, add, we get -7, multiply, we get -7/3, add, this gets a little hairy here, -31/3, add, -23, yeah, we had to get a common denominator for that 8, but anyway, here we go. It's not equal to 0. The remainder is not equal to 0 means that C equals 1/3, the number we divided by, is not a root of our polynomial. So we failed. But that's okay. We move on to the next number. I'm trying to be consistent, so I'll go to the next number in the order of the absolute value of them. So okay, we took the smaller 1/3. Now we're going to 2/3. We're synthetically dividing, and we're happy because look at this. We got a 0 remainder. Party time, party time. Because the remainder is 0, that implies that C equals the divisor 2/3 is a root of our polynomial. Now it tells us a lot more than that. So we found one root. We know there can be a maximum of 3, but we found one, and that is such good news. We are going to take that root and use it to start factoring down our polynomial. We're going to try to get it all the way down to first degree factors so we can read all the roots off of it. And where are we going to get the rest of the factorization? We take all the numbers and the quotient on the bottom row of the synthetic division, write it as a polynomial 1 degree lower than the original 3rd degree polynomial. So what I mean for step 3 is we're going to write the factored form of g of x as x minus the root that we just found, so it's x minus 2/3, times parenthesis, take the 3, -6, and -12 and write it as a 2nd degree equation, 1 degree lower than the original equation. All right, so we've got our q of x right here, our quotient. And let's see, we need to find the roots of the quotient of the second part. See, we already have the first factor that represents x minus our root c equals 2/3. So we want to factor the second parenthesis down to find the root of this q of x portion of our polynomial. Okay, to do that, we are going to make a new list of p over q for the new little polynomial. So it's going to be the plus or minus factors of 12 on the top factors of 3 on the bottom. So we get 1, 2, 3, 4, 6, and 12 on the top. Those are factors of 12 over 1 and 3 on the bottom. Okay, we have our plus and minus on the front. Hey, wait a minute. Wait a minute. This list should be a subset of our original list up in step 1, okay? And it's not. Our original, it should be a subset of the 1, 2, 4, 8 on the top and the 1, 3 on the bottom. And it's not. Now, why does it have to be? Because we're just continuing, all we're doing here is continuing the factorization of the original g of x. So, of course, we're going to have the same potential list of rational roots. All right, but it's not happening here, and that's an indication to us that there are no more rational roots available. So we can stop right here and say that we have found all the rational roots for this g of x. It's just the one number, 2/3. 2/3. Now that's the end of this question, but you know, if they had asked us to find all the roots of g of x, we could have gone further. And that's what I want to discuss right now. We could have gone further. If they had asked for all the roots of g of x, we would have found the remaining irrational roots of q of x, that portion q of x, which is 3x squared minus 6x minus 12, by using the quadratic formula. The quadratic formula would have given us values for the roots. When we plug it in, the values, let's see, we plug in a 3 for A, negative 6 for B, and negative 12 for C. Well, actually, we could factor it before we plug it in. We would factor a 3 out of the q of x, and then what would be left would be x squared minus 2x minus 4, and we would use those coefficients in the quadratic formula to further the factorization. So we'd have 1 for A, negative 2 for B, negative 4 for C, plug them into the formula and simplify. We would have ended up with 2 more roots, 1 plus the square root of 5, and the other root 1 minus the square root of 5. I'll write it as plus or minus, but it's really 2 roots. And the interesting thing is, it's so obvious. When a number is under a radical, it can never get out. Like 5 is under the radical, we could never get it out. We cannot simplify it out. That's an indication that this is an irrational number. Okay, so the 2 roots that we're missing from the maximum of 3 roots are irrational. They only asked us to find the rational ones. So we stopped at that big box where it says the rational roots for this g of x. It's only 2/3 and we're finished.